So could you tell us about who you are?
Certainly. My name is Davide Guzzetti. I was born and raised in Italy. I went to school there in Italy. I went to school to Politecnico of Milan, or Politecnico di Milano, which is one of the largest engineering school in Italy. After that, I got interested in astrodynamics during my master degree, especially during the senior design project. In the way the Italian education work is a bit different from the way American education works. So at least in my college experience, we did our senior design class actually during graduate school. And so during that time, I got exposed to trajectory design, and I got really excited about the idea of, designing trajectory and planning the motion of a spacecraft. And so I made that the topic of my master thesis. And during my master thesis, through my advisor in Italy, she had connection with some other professors here in the United States, and I was able to visit one of the laboratories here in the States, and actually at Purdue University. So I did part of my master's thesis research at Purdue in collaboration with Purdue. And I ended up actually applying for the PhD program there and getting a PhD 4 or so years later in astrodynamics. Mm-hmm. After that, I spent some time abroad again for a postdoctoral position. And then I came back to the States again, and now I'm an assistant professor at Auburn University.
So why did you want to become an astronautical engineer?
Excellent question. I was always fascinated by space, by the idea of, I was fascinated by the idea of exploring new worlds. And so what's the ultimate frontier for exploration? I mean, I guess to me, that is space. And so when I was on my senior year in high school and I was trying to figure out what to do in life, I started looking around. I decided, okay, how can I contribute to space exploration? And so I ended up speaking at the aerospace program, because at least in Italy where I grew up and in my region, we didn't have an undergraduate that focused specifically on space exploration. And I think even in the States, there are very few places that does. So becoming an aerospace engineer was sort of a gateway for me to then get involved with space exploration, which was the things I really care about, or at least I were really excited about. But that it was a struggle to decide what to become, what to do with my life. I mean, I changed ideas several times during the high school. I still remember during the high school period. At a certain point of my life, I wanted to be a computer scientist. A bit early on, I wanted to be an archaeologist. So I went all the way from archaeologist to aerospace engineer.
Mm-hmm. All right. So can you explain some of the things that would qualify a space environment as simple or complex?
Yes, I think I guess I'll turn the questions in saying that I think space is complex, period. I don't think there is any environment that I would say is not in space that I would say is not complex. I'll maybe say that there are environments with certain characteristics and environments with other that we have known for a longer time, or that we have gained more experience on those environments, and there are some that are uncharted, both in terms of, well, we don't have any spacecraft that has visited these environments, or from a theoretical perspective, we are still trying to understand how dynamics works in this environment. And I can make an example as, for example, Keplerian dynamics. Keplerian dynamics describe the motion of object, let it be a spacecraft or a celestial bodies, under the gravitational attraction of a single body. And you might have seen that in high school. I remember that being covered in some physics class I took. You'll certainly see that in college in an aerospace major. Those are not simple. They are complex, but we've been working on that problem since Newton's age, if not earlier. So we have 400 plus and probably much more than that of experience in dealing with that dynamic. So that's why they're maybe perceived as. Also have many spacecraft that has flown along trajectory that are in forced approximation Kepler and Earth. There may be other environments such as multi-body gravitational fields that are generated by the attraction of the gravitational of, let's say, the combined gravity field of the Earth and the Moon. We knew of the existence of those problems early on, pretty much at the same time as Keplerian mechanics were explored, but we didn't have necessarily those type of problems, and so that's why those problems might be perceived as more complex, and also there are some other dynamical reasons why they're more difficult. But again, I think every space environment is complex. It's just a matter of how have we get there on that specific problem. And I guess I'm a bit biased because I do astrodynamics, so maybe I interpret this question from the astrodynamics perspective, but space environments obviously is much more than trajectory design, how materials will survive to space, how you're going to generate power in space. It's just such a complex engineering problem. And so there is complexity in all these other aspects: power generation, thermal control, materials. And so on.
Right. So what are irregular gravity fields and what are the challenges working with them?
So that term could mean, I guess, different things. Irregular gravity fields could be fields such as, I guess, what would be the traditional astrodynamics interpretation of that term will be fields that are generated by a body, such as an asteroid, that does not have spherical shape. Something that Keplerian mechanics assume, I guess, is that the attractor is a point mass, so it does not have all the mass is concentrated at the barycenter, but simplify the distribution of mass. And that turned out to be a good approximation for bodies that are nearly spherical, such as planets. That's not the case for small bodies, such as asteroids. And if you happen to have seen the pictures coming back from observatories or from robotic missions, those asteroids don't have spherical shapes, and they're not even nearly close to be spherical. And so that generate what we in astrodynamics we call an irregular gravity field. Mm-hmm. And so dynamics becomes more complex because it becomes more nonlinear, and also there is a modeling challenge. It's just coming up with the math with the model and the math behind the model to simulate how the spacecraft will move those fields. Mm-hmm. And then there are other challenges because there are so many ways to represent a gravitational fields, and some model might work better for some, I guess, this mass distribution of mass, or some or in certain conditions such as the distance from the central body, and some other models might work better at shorter distance from the trotting body. Again, you have this. There is not a single. What is fascinating is that there is not a answer this type of problem. There are multiple models, multiple approach, and they'll have pros and cons that need to be traced and balanced when deciding which model to use.
Right. So how can strong solar radiation threaten to knock a space station out of its orbit?
So solar radiation pressure, it's essentially the interaction of photons which are emitted from the sun that reach us or reach a spacecraft from the sun, and actually they exchange momentum with the spacecraft. So they exert this very tiny pressure on the surfaces that compose the spacecraft. Now, the pressure itself, this tiny little push, it's really tiny. So it accumulates over time. Now, will it knock a station out of its orbit? That really depends on the orbit, on how which type of station keep moving, or most likely yes. But in first approximation, it really depends on the orbit that this space station is traveling to. Because in certain conditions, if you imagine the solar radiation pressure as a wind that blows toward in an orbit configuration, for half of the period, you might be traveling against the wind. But for the remaining half of the period, you'll be traveling in the direction of this wind, and so the average effect might be null on average. So it really depends on the orbit and the sensitivity of the orbit to this perturbation.
So what are some of the solar system robotic mission concepts that you're looking into?
I think one of the concept that we are currently that I'm really excited about is the attempt to utilize smart material, and especially smart polymeric material, to develop very large space structure, because it's very difficult to bring large structure to space, because the launch vehicles have so many room in their fairing envelope, so there is so much of a big spacecraft that you can load on a rocket, and you can try to pack that spacecraft, or you can try to fold that structure in intricate ways, so that when the spacecraft reaches space, it deploys whatever appendages or whatever system it needs to deploy. But even that, it's tricky, because the more mechanism you introduce, the more risky the mission become. And anyway, there is a certain limit to the size of the spacecraft you can do that you can achieve with traditional mechanical means. So we are taking, I guess, a very unconventional and I guess high risk, high reward approach in trying to see if these polymeric material that are able to change shape when they receive an external input could be leveraged to develop very large space structure. And for this type of research is conducted with another professor here at Auburn that, to give full credit, it's Dr. Millen, and it's his contribution. It's pivotal to this type of effort that we are conducting. And so our idea is to essentially develop kilometer-long tape of smart plastic, unfold this tape once in space, and then using this technology to fold this kilometer-long tape. You can imagine this as a meter tape into a shape that we need, or utilize this ability of the plastic to fold and simulated to deploy this structure that will be stored in a rolled configuration. And on this plastic substrate, we are also studying how we can embed electronics or payloads or things that you will need to perform your I guess your science mission or whatever mission you have. So we call this flat fabrication of self-assembling space system, because there are systems that can be designed flat on this polymeric substrate, and then they can sort of self-assemble or self-deploy in once in a while. Now, to be fully transparent, I mean, this is all extremely early on. We are still at try to understand if this idea even makes sense and if it's feasible, and how can we and what we can do, what further research we can do to get one step closer to this, for this idea to become reality.
Okay. So what has been your toughest accomplishment so far?
Good question. I think honestly, becoming an assistant professor has been one of the I guess toughest achievements of, at least of my career so far. Reason being that it's a complex application process. It's also fairly, I mean, I would say it's competitive, and so finding the right university, the right place, and being, I guess, preparing the entire application package, and also building your career or resume so that you can even qualify for this type of positions has been quite a challenge.
Right. Is there a big milestone that you're looking forward to in your research?
I would say so. I guess seeing that flat fabrication of self-assembly idea coming through, or at least getting one step closer to reality, that will be an important milestone. We are also exploring with other type of technology and try to bring that into astrodynamic or space mission design, such as virtual reality. One of my long-term goal will be to transition trajectory design and astrodynamic to immersive computing. So start designing mission into a virtual reality environment, or into an immersive computing environment. Another, and I guess very long-term and I guess aspirational goal will be to be able to teach a spacecraft how to behave. We're studying we are taking tools from the artificial intelligence community and see how those tools apply to our trajectory design problem. And what I became intrigued with is some of this AI tool needs human intervention or human input. And so can we teach a spacecraft to accomplish a certain task? That would be one aspirational goal of my career.
And lastly, to high schoolers like me and to younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
I think I'll just give some advice that is true in general, no matter which career you're pursuing. And first of all, I guess take it with a grain of salt, because what have worked for me, or like what I've learned, it might not work for you. All of this is very personal. So I might suggest something, but it might not work for you, or you might not like that approach. So feel free to completely disregard my suggestion. But I will say, first of all, know yourself. So try to figure out, use your early year in college, high school, to learn yourself, learn what you like. And so try to figure out what you would like to do when you grow up. And I would encourage you to talk to as many people as you can. Be proactive. Don't wait for opportunity to come to you. Otherwise, it will be the external world defining your career and not you trying to define your career. So if you can, talk to people, read up information online. Again, explore, learn, and try to figure out what you like and what you don't like. Once you do that, then you can commit, and you can commit to a specific career path. And again, same advice, be proactive. So seek out opportunity, plan your career, because you might be at some points when you're older where I guess it's never too late, but some career milestone can only be reached if you prepare, and they require some preparation. And so, the earlier you understand what you need to do to get to that career milestone, the earlier you can start actually working toward your goal. So, plan, maybe not in your early college year because you're still trying to figure out what you like and what you don't like. But maybe later on, when you're close to graduating and you're seriously starting to think about a career, I think it's a good time to start doing those 3 years plans or 5 years plan and start to, understand how and break those plans into steps that into action items or intermediate milestone that you can attempt to achieve. I think those are my 2 cents. Again, they might work or they might not work for you, but they're
Great. Well, thank you for coming here, and thank you for letting me interview you.
Yeah.
Yeah.
Thank you for having me. Again, take everything I said with a grain of salt, but hopefully there is some use in there for you if you're in high school or close to deciding where to go to college or what to do with your career.
Have a good day.
Thank you. You too.